How's it going? Hope everyone's doing alright today. Were there any questions over section 5.2? Yes, just email me the pictures of your work for part 1 project. Okay. Yeah, so make sure you get that done today, that you get those in for the project. You could send them through Canvas as well, whichever way you prefer. Okay. Alright. So we'll get started with section 5.3 today. I think we'll be able to do both 5.3 and 5.4, but we'll see how it goes. Okay. Alright. So we're talking about independence of events, and we're also talking about the multiplication, or at least multiplication rule we covered through section 3 and section 4. So we covered the addition rule in section 2 last time, And so this time we'll look at the multiplication rule. Before we look at multiplication rule, though, let's look at independent or dependent events. So two events let's call them E and F are considered independent if the occurrence of event E, I think there might be two R's there. Yep. Occurrence of event E does not affect the probability of event F. Okay. Now, this leads to what we call the multiplication rule for independent events. And this is ultimately how we would test to see if two events are independent. And so we would have to show that probability of E and F is equal to the probability of E times probability of F. Okay. All right. Now, when we have processes being repeated, such as, let's say we flip a coin 10 times, the outcome of the coin on the first flip, whether we get heads or tails, does not influence the outcome of any flip after that, whether we get heads or tails on each of the other tries. And so, repeated process of flipping a coin, those are considered independent events. So if we wanted to find probabilities there, we could just use this multiplication rule. Now, same thing if we took a six-sided die and we said, okay, what's the probability of rolling a 1 5 times in a row? And, you know, if one die lands on a 1, and then if we roll the die again, it doesn't necessarily change the outcome if we roll a 1 on the second time. You know, I mean, that's not influenced by the first one. So each time we roll a die, it's considered an independent event because there's really no influence from one time to the next. If we flip a coin and it lands on heads 9 times in a row, that doesn't mean it's any more likely to land on heads the 10th time, unless, I mean, as long as it's a fair coin, as we call it. Now, if we had two events and we're talking about our die, and one of our events is rolling a 1, and another one of our events is rolling an odd number, okay, maybe those are not independent, because there's some commonality that they share there. Okay? So we might say, for example, event A is roll a 1 on a die, and event B is we want to roll an odd number. Okay, so let's think of the probability of each of these. What's the probability that we would roll a 1? Well, as we generally calculate probability, it's the number of ways in which we would be successful out of the number of possible outcomes that we have. So if we roll a die, how many possible outcomes are we looking at? There's 6 total outcomes when we roll a die, and how many of those have a 1? Only 1 out of 6. Okay. Now we look at probability of B. What's the probability we roll an odd number? Well, we know there's 6 outcomes still. The question is, how many of those are odd? Well, we could roll a 1, 3, or 5. That's 3 different outcomes where it lands on an odd number, so our probability is 3 out of 6. We also want to look at the probability of A and B. Now, A and B means we both roll a 1 and we roll an odd number. Okay? 1 is an odd number. So, if event A, its sample space is just 1, and event B has a sample space of 1, 3, and 5, then they have the 1 in common, so that basically P of A and B is the one that they have in common out of 6 total outcomes. So there's only one number in common between the two events, and that's if we happen to roll a 1 specifically. So there's a 1 in 6 chance both events are considered successes. And so here's our probabilities, and so what we'll do is we'll plug in the probability of A and B equals probability of A times probability of B, and see if they're equal to each other or not. Now, what I've done here is I've put in a question mark over the equal sign because this is what we're trying to figure out. Are they equal or are they not? Currently it's unknown. So if we plug in the 1/6 here, and P of A was 1/6, and P of B is 3/6. Well, 1/6 is about 0.167. And 1/6 times 3/6 is 1/12, which is 0.083. Okay. So our conclusion is that those are not equal. Therefore, we can say the events are actually dependent. Okay. So just like we can use this to represent the multiplication rules for independent events, if this statement ends up being false, it means that We do not have independent events, and therefore they are dependent events, meaning that the outcome of one depends on the outcome of other or is influenced by the outcome of the other. And we can see that here because they share this outcome of this one, and certainly if one is true, then the other is true. Okay. If we happen to roll a 1, then we definitely roll an odd number. So there's an absolute influence between those two things. Okay. All right. So another example. What is the probability of rolling 4 5s in a row? Okay. In this case, we're rolling a die one at a time, and we're seeing if we can land on 5 4 times in a row. Now in this case, we know that the outcome is independent because we know as long as it's a fair die, the result that we get on the first roll does not influence the result that we get in the second roll. Just like if we're picking numbers from a hat, the number we get in the first attempt does not affect the number that we get in the second attempt, as long as we're putting the numbers back into the hat each time. But that's something we'll talk about in 5.4. What happens if we take the number out and then we choose again? That actually changes the probability, and it's a dependent event. So we have to be careful about that scenario. But if we're just rolling a die multiple times or flipping a coin multiple times, these are considered independent events, each coin flip or each die roll. So, again, there's a single 5 on each die, and there's 6 total outcomes. So in our first roll, we have a 1 in 6 chance of rolling a 5. On our second roll, we have a 1 in 6 chance of rolling a 5. Third roll, 1 in 6 chance. And fourth roll, 1 in 6 chance. We have a 1 in 6 chance every time. And now what the multiplication rule says, as long as these events are independent, we can multiply them together and get our probability. Okay. Now when we multiply fractions, we multiply the top numbers going across, 1 times 1 times 1 times 1. And we multiply the bottom numbers going across, 6 times 6 times 6 times 6. Okay. So we multiply 6 times itself 4 times. And that gives us 1296. And then we'll take 1 divided by 1296. And that is 0.000777. So a very small chance that we would ever actually roll 4 5s in a row. More than likely we see variety there than not. But we are able to calculate that probability using this multiplication rule. Okay. Now, at the end of section 2, we introduced the concept of complementary probability, and so I want to show you an application of that here that does prove useful. I did that backwards, I'm sorry. And this is a probability we see in various places. If we want to find the probability of at least 1, then we can use the complement to find the 1 minus the probability of none. Okay? In terms of which one is easier to calculate, it's actually much easier to calculate the probability of something not occurring than the probability of something occurring at least one time. When we say at least one time, that means it could occur once, twice, 3 times, however many things that we have. For instance, if we look at number 16 on page 277, Christmas lights are often designed with a series circuit. This means that when one light burns out, the entire string of light goes black. Suppose that the lights are designed so that the probability a bulb will last 2 years is 0.995. Let me write that down before we move forward. Okay, so 0.995, probability one bulb lasts 2 years. The success or failure of a bulb is independent of the success or failure of the other bulbs. So, A, what is the probability in a string of 100 lights, all 100 will last 2 years? Okay, so we have a string of 100 lights, and we want the probability that all 100 last 2 years. We know the probability of a single bulb lasting 2 years is 0.995. Okay? So, we look at it because we know we have the bulbs are independent of each other. It's given to us in the question in this case. We can use the multiplication rule here. So for the first bulb, it has a 0.995 chance of lasting 2 years. Second bulb, same story. Third bulb, same story. Oops, left out of 9. And that continues until we get to the 100th bulb, which also is 0.995. Now, according to our multiplication rule, we have to multiply these all together. So, what would be an efficient way of multiplying all these 0.995s together 100 times? Rather than just doing 0.995 times itself 100 times in the calculator, what's an easier way of doing that? Does anyone have that? Well, this is where we can use the exponent. Okay? If we have 0.995 times itself 100 times, like we have here, then we can write 0.995 to the 100th power. And we can put that into the calculator. Now, on a lot of calculators, it depends on what you have. Actually, I should probably get my other ones out, even though I like this one better. For the exponent button, we have this one here on this calculator. It's X with a little box. So I put 0.995 raised to the 100 power. So I just hit, so just between the numbers I hit this X with the box on it, and that put the exponent, mark the caret there. And it gives us our result. And we have a similar button on the graphing calculator. Although the graphing calculator, we just have a caret, so we do 0.995 caret 100. Oh, we hit 0 again. At any rate, we get our result 0.606 if we round to 3 decimal places. Okay. So we definitely, for these problems, it's useful to make sure we understand how to use this exponent button on a calculator, and how the exponent is connected to the repeated multiplication like we see here. So hopefully that's something everyone's familiar with, but let me know if it's not. Okay, so there's a little bit better than a 60% chance this entire string of lights makes it all 2 years. It's very likely, or not very likely, but there's a fairly good chance that one of them's going to fail, it sounds like. But that's question B. B, we want to find the probability that at least one bulb will burn out in 2 years. Okay. Now this is where it helps to use that complementary probability I talked about. The probability of at least one burning out is equal to 1 minus the probability that none of them burn out. Okay. Now the probability that none of them burn out, that all 100 bulbs last 2 years, that's what we just calculated in the previous part. Here, we had all 100 lights, and all 100 lasted 2 years, so none of them burned out, and we had a probability of 0.606. Just take that 0.606 and plug it in right there, and so the probability that at least one bulb burns out will be 1 minus 0.606, which is 0.394. Okay. And that's the easiest way to work that problem. In fact, it's the only way that we know how to work that problem. The other approach involves what we call counting techniques, which is a way more complicated question. Okay. But again, it's basically a formula that, anytime I say probability of at least one, we have to know that based on complementary probability, it's equal to 1 minus the probability of none, because having none burn out would be the complement of having at least one burn out. And that's the connection there to complementary probability. It's because these are complements, go back to what we talked about on Thursday last week. We know that the sum of their probabilities is equal to 1. Therefore, we can move things around and create a more useful equation, such as this one. All right. Done with that. Let's see. This is a silly question, but I like it. Let's look at 28. According to the Internal Revenue Service records, 6.4%, 2% of all household tax returns are audited. According to the Humane Society, 39% of all households own a dog. Assuming dog ownership and audits are independent, what is the probability a randomly selected household is audited and owns a dog? Okay. Again, kind of a silly question, but it certainly demonstrates the thing that we're trying to learn here, which is this independent events and the multiplication rule. Now, we said at the beginning, if we have an and statement here, and these two events are independent of each other, which we have been told that they are, and I would absolutely anticipate that they're independent, then we can say it's the probability of being audited times the probability of owning a dog. Okay? Because if these two events are independent, we just multiply their probabilities together. That's what the multiplication rule told us. So the probability that they're audited is 0.0642. Probability of owning a dog is 0.39. Just again, convert the percentages to decimals before we multiply. That's important. And then we just multiply them together from there. So 0.0642 times 0.39. And so it gives us 0.025. So roughly 2.5% of households are audited in a given year and own a dog. So anyway, let's move on to the next section. Section 5.4 is on what we call conditional probability. And the general multiplication rule. Anyway, so the concept of conditional probability is that if events happen to be dependent, meaning that the occurrence of one affects the occurrence of the other, then how we calculate probability changes. Okay. So let's look at conditional probability. And the idea here is that, let's say that event A, we know event A has happened. What then would be the probability of event B also happening at the same time? So event A has occurred. What then is the probability of event B occurring at the same time? Okay? So the probability... Well, first of all, this is our notation. This is the probability of B given, that's what the vertical bar means. So probability of B given that A has occurred. Okay. So anytime we see this, we think B given A, that means A has already occurred, and now we want to find the probability of B occurring. Now, if they're independent, probability of B occurring given that A has already occurred is simply the probability of B. Okay, because if there is no influence between the two events, the occurrence of one does not influence the occurrence of the other, then the probability of B, given that A has occurred, B doesn't care if A has occurred or not, so it's just the probability of B. But if they're dependent events, the probability that B occurs given that A has already occurred is the probability of A and B divided by the probability of A. Now, what this really amounts to is that, first of all, we have to know how likely it is for A to have occurred in the first place. That's what P of A is on the bottom. And of those scenarios where A did occur, how likely is it for both of them to occur then? And that gives us the probability of B given A. And so this is really the one that we want to focus on in this section. We already talked about independent events in the last section. This time we're a little more focused on dependent events. Okay. We don't necessarily call them that throughout this section, but that's really what's happening, is that they are dependent, and therefore the probability of B occurring changes knowing that A has already occurred, and that A is successful. Okay, and this is a formula, and when it comes time to do the test, I will provide this formula as part of a formula sheet for you. So don't worry about that. All right. So this is our formula for conditional probability. Now, this leads us to what we call the general multiplication rule. And the general multiplication rule this says that the probability of A and B is equal to the probability of A times the probability of B given A. Okay? Now, what we've really done is we've taken this formula and we took probability of A on the bottom, multiplied it on both sides, which canceled it here and moved probability of A up to the left-hand side. And then I switched the sides after that. So, essentially, this is the same formula, just with the terms moved around. So it comes from this conditional probability formula. But the idea is that, this works whether the events are independent or dependent, because we said before, if the events are independent, probability of B given A is just probability of B. And if they're independent, that's basically the same formula we looked at in the last section, okay, where we have independent events. If it's dependent, we do have to make sure we incorporate that. Like, how does the probability of B occurring change if we already know A has happened successfully? Okay. And it does change if they are dependent events. Okay. Let's look at my sock drawer. I think we talked about it a little bit last time. We'll go into a little more detail here. Let's suppose this is all theory at this point, because I'm just, for the purpose of the problem, I'm completely making up what's happening in my sock drawer, for the most part. Let's say that in my sock drawer I have 100 socks total, which, again, that's an exaggeration. But let's say, after I do laundry, I just throw them all in the drawer loose. I would not recommend this, and eventually it becomes a fixation. So, anyway, let's not dwell on that. But let's just say we throw the socks in loose, and they're all unmatched, okay, which would be chaos. But here we are. Now, in this drawer, among these 100 socks, I don't have a lot of color variation in my sock wardrobe, so I'm just going to go with white, gray, and black. That's actually the truth, because this is a guy thing, I guess. I don't know. My dress socks are a little bit more fancy, but yeah. Let's say most of my socks are white. That's also true, just because it's easy and whatever. Let's say that I have 65 white socks. Of course, I'm missing one. Probably multiple ones there. 25 black socks, and that leaves 10 gray socks. Now, the other issue is that we're not going to be looking when we pick socks out of this drawer, which is completely illogical, but we're going to say, okay, we're just picking socks out of the drawer in the dark, and we're going to pick 2 socks from this drawer without replacement. Now, without replacement is a phrase that we use in statistics, saying that when we randomly select objects, they are taken out of the selection pool, and it changes the number of items remaining, and it changes the probabilities for what's remaining also. So when we say without replacement, after the first selection is made, we don't put it back into the drawer. My problem is actually when I'm going to put my socks together after I do my laundry. My problem is I have so many different styles of white socks, and it's not that I have 65 white socks, but I don't know how many I have, but it's that I have 8 different styles of white socks. So that's what makes it difficult to match the things up, unfortunately. Anyway, I could probably solve that problem just by donating them all and then buying all new pairs of the same style, but I'm also really lazy and cheap, so yeah. Anyway, I see no reason to give away good socks. Alright. It's my fault for not buying identical styles in the first place. So, we're doing this without replacement. We're selecting 2 socks at random. So, first scenario was the probability of selecting 2 white socks. Okay. Now we break this down into, 2 different probabilities. The probability we get a white sock on the first try, and the probability we get a white sock on the second try. Now, we have 100 socks in the drawer. What's the probability that we choose a white sock? Again, when we think about probability, we think with a number of ways that we could be successful out of the total number of possible outcomes. So we know there's 100 socks in there, but how many of them are white? Okay, so it'll be 65 out of 100. So, of the 100 socks, there's 65 that are white, so 65 out of 100 is our probability of selecting a white sock. But here's the issue, and this is where our conditional probability comes into play. The idea here is that once we choose that first white sock, we take it out of the drawer. We want to keep that white sock and then choose another white sock so we have a pair to wear the next day. So if we take that white sock out of the drawer, there's only 99 socks remaining. Okay. How many of the remaining socks are white? Okay. So we had 65 in the original selection. Right, it could be 65 or 64 depending if we got a white sock first. In this case, we're saying we absolutely got a white sock first. Otherwise, we wouldn't be drawing again to get another white sock. And so that means there's 64 left that we could get out of the 99 remaining socks. Okay? Because we're looking at the probability of getting a white sock the first draw and the probability of getting a white sock on the second draw, assuming that we got a white sock on the first draw. And that's what the conditional probability is all about. On the second draw, we already assumed that we were successful the first time, which it had this probability. And then what is our rate of success on the second try then, assuming this was a success? Well, that means there's only 64 white socks left over now out of the 99 remaining socks. So what happens is our probability of success decreases the more socks that we take out of this drawer, of that color that we want. Okay. Not that we would ever take more than 2 out. It would be weird. Um, but I could change it from socks to jelly beans, and we can do as many times as we want. Jelly bean jar, not drawer. Anyway, well, yeah, that's the whole point of the conditional probability, is that, you know, assuming that we were successful the first time, how does that change our probability for the second draw? We got a white sock in the first draw, and then if that happened, what's our probability of getting a white sock in the second draw? Well, that's now 64 out of 99. Now we multiply it across, and again we multiply the numerators together and the denominators together. So it's 65 times 64 and 100 times 99. And then we'll work that out, and we'll just divide. $65 times 64 is $41.60 over 9,900. And then divide. And we get a probability of about 0.42. So there's really a 42% chance that we just pick 2 socks at random and we have a matching pair of white socks. Which is not bad. But that is the most numerous color of socks in our drawer. Okay. Let me run out of room in this paper. I'm going to flip over to the back. So again, we have 100 socks, 65 white, 25 black, 10 gray. Alright. So next example, what's the probability we select a gray sock and then a black sock? Not that this would be helpful for us getting dressed in the morning, but let's look at the scenario and see how it works out. What's the probability we choose a gray sock at random on our first selection? So the first one's going to be gray. We know that we have a 10 out of 100 chance of getting a gray sock. Okay. And then we want a black sock on the second draw. Now, we have a few more black socks in the drawer than we do gray. 25 in fact. Now, we've removed the gray sock from the drawer, which means there's 99 socks remaining, but now 25 of them, all 25 of the black ones are still in there, so it's 25 out of 99. So in this case, the bottom number decreases, but the top number doesn't decrease because we still have all of that particular color in the drawer. If we ask for a gray sock again on the second draw, this would be 9 instead of 10. Well, because we went to a different color, we still have all of that color remaining because we chose a gray the first time, but all 25 black socks are still in there. Okay. So that ends up being 250 out of 9,900. And that's 0.025 once we multiply that. So this is a lot less likely to occur, but that's because we're working with the two least numerous colors in the drawer. Okay. Let's see. Now, this is not really a probability question, but I'm just seeing how clever everyone is. How many socks would we have to draw? How many socks do we need to pick to make sure we have at least one matching pair? How many socks we need to pick? And we don't care what color pair of socks we get as long as we have a matching pair. What is the minimum number of socks we'd have to pull out of this drawer to guarantee that we are holding a pair of the same color in our hands? Anyone got that? And again, this is not really a statistics question. I'm just seeing what everyone thinks, or just giving a mental brain teaser kind of thing. In order to guarantee that we have a matching pair of socks, we would have to select 4 socks. That'd be the minimum number. Because what happens is, if in our first 3 socks we pick one of each color, then the 4th sock has to match one of those first 3. And that's the worst case scenario. It's possible that the first 2 socks are the same color, they're both white. As we saw before, that was a 42% probability. But, worst case scenario, the first 3 socks we choose are all different colors, and the 4th one would have to match one of the first 3. Okay? I always like to ask that question to see, and it's really, again, not a statistics question, it's more of a being clever kind of question. How would we, and this is back to statistics, how would we go about finding the probability that we get a matching pair on the first 2 socks? Okay. So we don't necessarily care what color, especially if we're using these 3 colors. Probably we don't really care too much which color we're using. But what's the probability that we get any matching pair in choosing those first 2 socks? Now, that means we either want 2 white socks, 2 black socks, or 2 gray socks. Okay. And so we would calculate the probability of each. And we would just add those probabilities together, it turns out. The reason that we add them is we want any one of the three scenarios to be true. Okay, we don't care which of the three scenarios is true, we just want one of them to be true. And so we add their probabilities and we see what we can get. Okay. Now we already know the probability of getting 2 White Sox was 42%. That was the first problem we did. But again, that's 65 over 100 times 64 over 99. For 2 Black Sox, it's 25 over 100 times 24 over 99. And for 2 Gray Sox, it's 10 over 100 times 9 over 99. Okay. That's 600 in that one. So 4160 plus 600 plus 90. So we get 4850. Out of 9900. So we have about a 49% chance overall of getting a matching pair just by picking 2 socks at random. Which is not bad. I guess if we pick socks from a drawer in the dark, that's not bad for that scenario. Yeah, it's not particularly a realistic example, but I think it nicely illustrates this concept of conditional probability. So if we draw 1 White Sock the first time, our second probability is conditional because it changes based on the fact that we already picked 1 White Sock from the drawer. So it changes both of those numbers accordingly. Okay. And the same is true for each of the other scenarios where it's either both black or both gray. You know, getting 1 the first time certainly influences getting the second one of the identical color the second time. Okay. Now, this one we kind of use the conditional probability in a more logical sense, I would say, rather than really relying on the formula. This is more of a logical approach, which we can do in this scenario where we have we know how many of each item we have, and we're making multiple selections like we're doing here. Now, there's another type of problem that we could work here. And it's kind of like how we talked about it in section 5.2. There's really 2 different ways we can see the addition rule and how we apply it, and whether it's a scenario where we can just calculate everything ourselves, or if we're given a table, if there's a lot of different data values, that's the other scenario. It's really the same thing here with conditional probability. So, I have another table for us, and we just have a few minutes. This problem 36. close enough. We have rows and columns for total at the end. Which I usually draw with a double line myself. It generally is going to be in bold print if you look in the textbook. We have different age ranges, 17 through 29, 30 to 44, 45 through 64, and 65 plus. And we have party affiliation, Republican and Democrat. So we have 4,000 people total in this survey. Basically just surveying people's political parties. Now, there's some different things that we can ask here, but I want to focus on the conditional probability since we don't have a lot of time left. But we could ask all the same questions we talked about before. What's the probability that someone's Republican? 2,200 out of 4,000, whatever that works out to be. What's the probability someone's between 30 to 44 and a Democrat? So 30 to 44 and the Democrat, there's 384 people out of 4,000. That's the and statement. We can do an or statement. But I want to focus, that's all the stuff that we covered in the section 5.2 last time. What I'm saying is we can take the same data and ask a conditional probability question as well. And again, let me remind us of the formula for a conditional probability. Probability of B given A equals probability of A and B over probability of A. So, for example, what's the probability that someone is between 45 to 64 given that they are a Republican? Okay, so that's our B and that's our A. Now, we know for the numerator, we look at what's the probability of A and B, that someone is both 45 to 64 years old and a Republican. That is 1,075 people right there out of the 4,000 total. And then P of A on the bottom, what's the probability that someone is a Republican? We said that was 2,200 out of 4,000. Now, we end up with this fraction, 1,000, basically two fractions inside of a larger fraction. But what happens is that because these both are over 4,000, the 4,000 ends up canceling, and we end up with 1,075 over 2,200. And then that works out to give us 0.49, 0.489. That'd be better. The 3 decimal places again. Probably the best way to do it. 3 or 4. So about 49% of the time, given that we selected a Republican, about 49% of that group is going to be in the 45 through 64 range. Okay. Another question is that we could ask, and let's switch it around. Find the probability that a person is a Democrat given that they are 17 through 29 years old. Okay. Part of it is understanding how the language here works. So we're finding the probability that someone is a Democrat given they are in the 17 to 29 age range. Okay, this reversed it to where we wanted the probability that someone was in the 45 to 64 age range given that they were a Republican. So it changes which one we assume. This time we're assuming the age is a certain range, and we want a prediction about the political affiliation. So first of all, on the numerator we pick the probability of both occurring, so Democrat and 17 through 29. 17 through 29 Democrat, we see it overlaps here at 184 out of 4,000. And then on the bottom we put the probability of whatever came second, which is the 17 to 29 year old range. 17 to 29 year olds make up 408 of this group out of 4,000. Okay, we know the 4,000 are going to cancel here, so it's 184 out of 408. And we end up with about 0.451, so a little better than 45% of 17 to 29 year olds are Democrats. That's what that really tells us. Okay. At least based on the survey. Alright, let's look at homework. Again, we have 2 pages that we covered today. Sorry, I went too far. Let's see. So first of all, on page 277, look at 11. $17. $25. Then on page 286, let's see. I'm real picky about these problems, I'm sorry. 27. $29. I'll go ahead and do 36. Alright, sorry about taking so long there. I wanted to pick problems that best represented how I wanted us to learn these things. So, anyway, so check out those, and we will continue from here on Thursday. Probably the week after next, we're looking at having another test, and I should have your test graded for this class later today. So, please look forward to that. For project 1, you can either basically take pictures of your work if you did it on paper, and either email it to me or send it through Canvas. And if you actually, either way, just email it to me or send it to Canvas, whether you did it on paper or if you actually typed it in the computer, whichever way you did, just send it to that way. So, okay? Make sure you get that done today by the end of the day. Awesome. Okay. Well, y'all take care, and we'll do this again on Thursday. Have a good day.